fields. I guess, other than the book, I only gave you one example, right? I said, let's talk about Newton's law of gravitation, right? So the way it's written in the box, that's a vector field, right? It's a function, but at each point, x, y, z, that function spits out what? A vector, right? And so, I mean, I guess I could show you the pictures in the book again, but basically they were showing space, but at particular points they had these red arrows drawn. Do you guys remember that? So that's what a vector field is. It's at any particular point we have a magnitude and direction. Based on gravity, right? Yeah.
Are vector fields mostly only done in Cartesian coordinates? Could we do it in polar?
So anything that's in, that's a good question. Anything that's in Cartesian, of course I can change to other coordinates, spherical. Your question is that done regularly for any particular example? I don't know.
I noticed you converted, you know?
Yeah. I will say this. I guess I don't know when and if we use polar. If we're going to integrate, of course we would at times, right? But I will say that one idea that comes up here that we visited before is the idea of parametrization. When we studied the first chapter of the course, do you guys remember we used to do vector valued functions? Like, do you guys remember doing this? R of t. You guys remember that? So what was this? This was x of t and then y of t, right? And then if it was 3 dimensions, we also had a z of t. You remember that? Okay. So I think there's some parallels to what we did then and what we're going to do now. Actually, these curves are coming back actually today. But I guess what I wanted to say is, do you remember how t was your parameter? It represented speed, right? You could change the parameter and still be on the same curve. So I think my initial answer to your question is, I don't know. But what I do know is these things, if we think of these as functions of some parameter, we will often change the parameterization to be more convenient. I think that's done more than actually just changing coordinate systems. Okay? You know, another example, well, I don't know if I want to write it down. Well, I'll show you. Marvin and Duncan both worked on electric fields for their project was based on chapter 15. So they had a lot of double integrals, triple integrals to do. But I don't know that they really had this. Coulomb's law. You guys know Coulomb's law? How many people know this law? Yeah? I don't. You should see me asking my daughter today. She's in physics. She's like, I'm like, okay, tell me everything you know about electricity. So I'm going to go teach vector fields today. Right? Coulomb's law says the electric force exerted by the charge on a that's what she asked me. She said, are you talking about a point charge? I said, well, yeah. So suppose you have a positive unit charge, right? Charge of 1 at some point. Coulomb's law says this. I asked her, I said, do you guys have any formulas that have a little 3 halves exponent in the denominator? Did you guys have any of that in physics?
But all of the physics formulas.
Well, okay. It seems to always show up. You guys, next Monday we'll kind of talk about why that happens and what's significant about it. I mean, I think you have some of the story, and I think you're going to get more of the story. So I hope that you'll find that encouraging. But anyways, this could be seen as a vector field, right? Because you could talk about the charge at any particular point in a space. Let's just leave it at that. Because I'm beyond my area of expertise when I start going that route. Thanks a lot, Aaron. Okay, any other questions? Well, let's look at what we're going to do today. Let's move beyond that. Let's zoom out and let's look at section 2. So section 2, line integrals, right? And I like a couple of the pictures that they have in the book. So again, the symbol we're going to use, right? We're going to have an integral symbol, but you'll know it's a line integral because you're going to see a little C down here, which stands for curve. Okay? Here, let's go back to Calc 1, and let's give you one of the most basic examples of an integral. Let's compute it. That usually gets students in Calc 1, because they're like, what? What am I integrating? So, of course, the answer is? Okay, and so you get x. And so you are integrating from a to b, and so the fundamental theorem of calculus says that this is b minus a. Okay, what did we just do? Let's explain that to a Calc 1 student. What did we just do? Well, let's show them, guys. Here's A, and here's B, right? And what did we just do?
The area that number line is.
Well, yeah.
Distance.
We did. We found a distance, didn't we? The distance is b minus a. Of course, what we did, of course, is we integrated 1. And so you could also say, well, you found the area under the curve. Of course, if you pick 1, what's really nice about that is that the area is the same as the distance, right? It's like having a tape measure, right? And so I agree that this distance from here to here is b minus a, right? We integrated 1. Okay. So what's going to happen now? What's going to happen now is I'm going to have some curve. And what I'm going to somehow be doing is, well, for example, you're going to, if you choose the value of 1 for your function, you will be measuring the length of the curve. You'll actually be computing the arc length. That's what a line integral is in the very special case that you're integrating 1. But now in general, this is not the first picture you show a Calc 1 student. Maybe the first picture you show them, at least if you're in my class, you might show them a parabola, right? Or something like that. And you explain to them that, oh, Calc 1 student, when you're integrating between A and B, and you want to find the area under the curve, but you can't exactly, so what do? We divide AB into, yes, we get these rectangles by dividing into n subintervals, right? And for each subinterval with width, let's say delta x, right? And then when you mention rectangles, somehow you're deciding how you want to build those rectangles. I don't know. You pick a point at each interval, right? And then what you do is you sum up, right? What? You sum up the delta x's. Oh, that's the width. What else do you need?
The height.
And the height, of course, is, well,
Defined by the formula.
yeah, if this is f of x, then the height is f of x at that point, right? And so you have to put a little star or a k or something, and then you say k equals 1 to infinity, and you say if we take the limit as the size of the partition goes to 0, that's an integral. Right? You guys did that in Calc 1. Well, we're going to play the same game now, but instead of dividing AB into n subintervals, we're going to divide a curve into little pieces. And let's see how that works. There's a nice picture here. Where did it go, though? Remind me. Right under here. Scalar line integrals in the plane. Kaboom. Ah, yes. So they say take this surface, right? And on the surface we have a curve, right? So if I remove the surface from the picture for a moment, just concentrate on the curve, and then you have underneath the curve is a curtain, right? And you know, between some A and between some B. Guys with me? And so maybe what we're really finding here, well, we know that integrals give me the area under the curve, right? So again, you could see maybe how there's a relationship between what we've been studying and what we're about to study. It's all about doing a Riemann sum again. So what do? Well, isn't this what I just did in Calc 1? Yeah, except you'll notice I changed variables. What variable am I using? S. Do you remember what S stands for? Arc length. So one of the things we learned how to do is we learned how to parameterize a curve in different ways. And I told you guys way back then, hey guys, it's really good, it's a good idea sometimes to parameterize by arc length. Well, we're going to bring that idea back again. Okay? And if we have a curve parameterized by arc length, then, so you'll notice that's why they wrote this. They wrote x of sk and y of sk. Remember, x and y are going to depend on a parameter. We want them to depend on arc length. Then, the area of the curtain is approximately this, which of course is a Riemann sum. And if you have a Riemann sum, fundamental theorem of calculus works, right? And so here's a really nice picture, right? That's approximately the area of the curtain, right? What can I do? That's A and B. I can increase, isn't that, hold on, sorry. How about showing me the whole demo? There we go. I can increase n, that's what I wanted to do, right? And now for a given n, you pick which k you want, and we can compute that area. But as n gets bigger and bigger, right? Or you can make it go to, you can make the size of the partition go to 0, and then you have this. And then you can also destroy the app. That's kind of cool. All right. So this then is the definition of the scalar line integral, and they say in a plane, okay? It's once again the limit of a Riemann sum. The difference is we're talking about a curve parameterized by arc length. And so I have to go back to chapter 14 and relearn a little bit about those curves. That's actually good. So we have a final exam coming up anyway. Right? And then look at all the notation they have right there. There's like 3 different ways of saying the same thing. The most compact would be FDS. Okay. So I want to do some examples here. Oh, I don't want that to happen. Okay. So, average temperature? Yeah, it's okay. We could do that. I think my computer just went on the fritz. This could be problems. Let's do that as an example. So they want me to do the line integral c x squared y ds. Okay. Where c is the line segment from, well, let's say 0, 0 to 2 square root of 2, comma 2 square root of 2. So it doesn't quite say this, but close enough. So let's draw a picture. Here's 0, 0. And of course, 2 square root of 2, that would be the diagonal, right, of a square of sides 2 by 2, right? You can work that out with the Pythagorean theorem. And sometimes, in some applications, we'll actually talk about what we're going to orient the path that I'm taking, right? So again, this is not quite this picture, right? I don't have a crazy curve yet. I'm starting with a basic example. Okay? So I guess the question is, well, how do I compute a line integral? Right? Because you don't sit there and take limits of Riemann sums, right? We've seen that. We have the fundamental theorem of calculus allows me to take integrals. So the trick is to use the parameterization by arc length. That's what I mentioned. Okay? So if we go back to the example for a minute, right? Take a look at their solution for finding an average temperature. Well, they're just saying what x equals and what y equals, and they're plugging in, and we get something really nice, right? But how did this work? Well, in their particular example, r was equal to cosine s sine of s, right? Now, what about for us? Well, for us, we're doing problem 4 from the homework, or 14. And so I guess my first question is, can I describe this line? Well, I know it's y equals x. Yeah. How do you describe a line parametrically? Well, yeah, I do.
T always ranges from 0 to 1.
Okay.
You have your initial points, which in this case are 0 and 0. And
Okay.
so what's it going to be? It's going to be x times, x equals t times root 2 times 2, and then y would be the same as that.
So that's interesting, right? I mean, certainly I could do this. There's a parameterization. X equals t and y equals t. But I'll notice you said we want to multiply by root 2 over 2, you said,
Yeah.
right? Or divide by radical 2 is the same thing,
Oh, okay.
right? Why? Well, because what I want to have happen is that I measure the arc length as I move along, right? So, well, for example, what is the length as I go from 0 to 1, right? So here, I guess what I want here, if I want to go this whole distance, I would want t to range between, well, let's do s. Let's do s, I'm sorry. I want s, not t. And why do I want s? Because what I want, guys, is I want the square root of x squared plus y squared to be 1. We want this. We want the arc length to be 1. Right? And so the square root of s over 2 squared, no, s over square root of 2 squared plus s over square root of 2 squared. Sure enough, that's the square root of s squared over 2 plus s squared over 2. I get s, right? I get the arc length, so 1s, right? This is what we really want. I don't think the book explains it that way. I mean, if you take a look at the problem they give you at the start here, they just tell me, hey, evaluate number 14 where, here you are, s over square root of 2. Oh, wait a minute, there's a mistake I made. They say 1 minus s over square root of 2 for the y values. Why? Oh, because they're doing a different problem. Looks like I was doing 13. I did a hybrid. Darn it. I did a hybrid version of the problem. Well, let's do mine anyways, right? So here we go. What's that? How's this going to work? Well, we'll just try to do it, right? So number 14. Interesting. Hey, actually, let's do 14 and then we'll compare to what I said. I think that's smarter. So if we had, again, line integral over c, and let me write it down with you again, and let's get it correct, x squared y ds, and c is the line, r of s, which is given by, again, it was s over square root of 2, but now this other one we have 1 minus s over square root of 2. So actually, let me graph where that's going, right? And they tell me that 0 less than or equal to s less than or equal to 4. Okay? So let's see. If I plug in 0 for s, let's see. I'm at 0, comma 1, right? So it starts at 0, comma 1. If I plug in square root of 2 for s, I'm at 1, comma 0. Right? And that makes sense. Actually, guys, look at this square that we have on the graph paper. How long is that part of the line segment? That's radical 2. And remember what I said? I said this is s is 0, this is s is square root of 2. So that's a good thing. Now we're supposed to go all the way until s equals 4. And I'm pretty sure it's a line. So let's see if that's correct here. Here I'm getting that if I plug in 4, I'm at 2 radical 2, which is the square root of 8. Okay? So that would be, when s is 4, I would be at 2 radical 2, and which is, or square root of 8, let's say. Maybe is an easier way to say it. And then comma, we have 1 minus the square root of 8 here, which would be negative for sure. So I guess the path I'm following is this red path right here. Okay. But if I'm given the parameterization, now I can go ahead and substitute in. So here I go. We're going to integrate. And so x, of course, is given by s over square root of 2, and that's being squared. And y is given by 1 minus s over square root of 2. That's not being squared. And then we have ds. Okay? So it's interesting because I wrote it as a line integral, but if I can plug in the parameterization, now this is good old calculus, regular old integral. Okay? So let's finish up. I'll square this. I got to simplify a little bit. So I get s squared over 2 times 1 minus s square root of 2 ds. You might not like my s's look like 5s. Oh well. So let's see. I'll distribute through, and this is 1/2 s squared minus 1 over 2 square root of 2 s cubed ds. Okay. And so I get, let's see, this would be 1/6 s cubed minus, and then this would be 1 over 8 radical 2 s to the 4th, right? Oh, what are our bounds? Well, we were given that, right? We were given that. So when does that happen? It should happen immediately. When I switch from a line integral to a regular integral, I should be writing these 0 and 4 as my parameterization. And so, yeah, now I'm in good shape. I can do 1/6 of 4 cubed minus 1 over 8 radical 2 of 4 to the 4th. Okay. And we get what we get. I'm going to leave it at that. Okay. But at least you've seen a computation. Okay. I'm already past 10:50. After break, I'm going to show you guys some of the ins and outs of what happens when you don't have that parameterization convenient for you. Okay, so we'll show you guys that next. So when we were doing 14, I got this far, and I said I'm done, but I don't have to be done, right? 4 cubed is 64, right? So this is 64 over 6 minus, and this is 1 over 8 radical 2 times, well, this is 256, right? 4 to the 4th. And so some canceling happens, and I get 32 thirds minus, and here some canceling happens because I think 8 goes into that, right? Yeah, 32 times 32 over the square root of 2. All right, let me leave it at that. That's good enough. So at least we're somewhere that we can. We're going to do a redo. We're going to do a redo on this problem. Okay? And so you'll notice that I'm looking at the problem, okay, again, but I'm deliberately leaving the original equation off the screen. Okay? Oh, there it was, right? Here, let's do problem 14 again. I'm going to integrate along the curve x squared y ds, but I'm going to cover up that. And I'm just going to look at the picture of the curve. Now, if I asked you what's the equation of that, quote, curve, actually, I could ask my beginning algebra students that one, right? And they would all say, oh yeah, we could do that. That's a line. What's the equation? Negative x plus 1. That's my curve, right? Now, the beginning algebra student would not know how to parameterize a curve, okay? But you can do that. You can parameterize any curve very simply in the following way. We just say x equals t. and then we say y equals, well, if we throw a t in there, you could either write negative t plus 1, or I could write 1 minus t. Right? Are you with me on that idea? Okay. And then the only thing I need to do here is I need to figure out, just like I did here for various values of s, right? I need to figure out what would the t values be as I move from one point to another. That's not hard, right? Matter of fact, t should be between what and what to move along that line? Well, since t is the same as x, it's easy. You just look at the x coordinate, right? So 0, right? If I plug a 0 in, let's double check. Yes, I'm at the point 0, 1. And what's the maximum value of t we want? Square root of 8. And then the y value would be 1 minus square root of 8. You could see it, right? So this is another parametrization of movement along that line in this direction. It is not arc length speed. It's not unit speed. It's a different speed, right? If you think of t as seconds, right? How long is it going to take me to move? Think of t as seconds, it would take me square root of 8 seconds. Whereas the last time we did the problem, if I think of s as seconds, it would take 4 seconds to move along the line. It would take longer, right? This is less than 3. This is moving faster. Are you with me? Okay. So then the question is, can I evaluate the line integral when I have a different parametrization? And this will happen quite often. Quite often, we'll have a parametrization of the curve, but it might not be arc length parameterization. But you can still get away with it if you do the following, okay? So what I'm going to do is I'm going to convert this to an integral dt. And the way I do it, guys, is I have to use a fact. Fact. ds dt. Do you remember what that is? We did that back in chapter 14. The derivative of arc length with respect to time, that's speed. It's the length of the velocity vector r prime of t. Are you with me on this? So I'm going to have the following. I'm going to write this as, this is the integral, as t ranges from 0 to square root of 8. We decided that would be it. And I'll need to write, well, this. And where it used to say ds, I will write length of r prime of t dt. So let's think of what's going on here. Let's see. Well, again, how does this all work? R of t, that's, of course, the vector x of t, y of t, right? So what's r prime of t? Well, wait a minute. Before we do that, in our example, what's r of t? X of t, we said, is t. Yeah? And y of t is 1 minus t. Right? So that's r of t. Okay, now I'm ready for r prime of t. R prime of t would be the vector, oh, look at that, 1, negative 1. Actually, this is a really nice, easy example. When you look at movement along the curve, if I said, hey guys, what does the velocity look like? Well, it moves right along the curve, right? It's going like 1, negative 1. You don't really have a tangent velocity when the thing's a straight line. I mean, it's just part of the line. Okay, so now what? I need the length of r prime of t. And the length of r prime of t is square root of 2. So again, what's going to happen here is I'm going to have x of t squared, because that's what x is, parameterized by t. I'm going to have times y of t times the speed r prime of t dt. Okay? It's also sometimes called the arc length element, this little thing you have to multiply by to change to a different parameterization. What's that?
Kind of like a Jacobian.
Well, yeah, it's a fudge factor like a Jacobian, but it's not a Jacobian. Yes?
So if the magnitude of r prime of t is ds dt,
Yes.
then the bit at the end simplifies to ds still, right?
That's the point. Yeah.
Yeah.
This ds just became this.
Mhm.
Just like in the world of u substitution when you change your dt to a du or something like that, a dx to a du. This is a way that sometimes makes these things easier to evaluate.
Okay.
Actually, I'm going to be saying that over and over again this chapter. Now here's a way that makes them even easier to evaluate. Okay, it's kind of funny how this all works. But this is a nice trick. And so what happens now is you get, let's see. Well, we're integrating from 0 to square root of 8. What would it be? So this is t squared, right? And then y of t is 1 minus t. That's not too bad. And then square root of 2 dt. I like that. So I'm going to integrate from 0 to square root of 8. I'll bring the square root of 2 out front. T squared minus t cubed dt. Is this easier? I don't know. Let's zoom in a little bit, finish the calculation, and you guys tell me what you think. It's not easy to get it on the screen. There we go. So I have, let's see, the square root of 2 times, what would this be? This would be 1/3 t cubed minus 1/4 t to the 4th, right? And the t values I have go from 0 to square root of 8. So let's see. If I plug in square root of 8, and I'm cubing it, so that's 8 radical 8. But, okay, I guess the way to see it is, if you distribute the radical 2 to this stuff also, so 8 radical 8 times radical 2 is 8 radical 16, which is 32/3. You could see it. Maybe it's easier to see here. What's the square root of 8 if you take it to the 4th power? I guess it'd be 8 squared. 64 divided by 4 is 16. So you get 16 radical 2, which is exactly what that was up there. I mean, you get the same answer. Okay. I don't know which way is easier per se. I just want you to see that you're going to get the same thing. I think that's important to show the first day we do these. So there's other important things to show the first day we do these. These are very simple curves, right? I mean, this was a line, okay? Things do get more complicated in a number of ways. What ways? Well, look what we did so far. We did scalar line integrals in the plane. We are also going to do line integrals in R3. Does this box present any challenge for you? Besides the fact that every problem is going to be longer. It's exactly what we just did, right? I guess we have the arc length element again, the square root of x prime plus y prime plus z prime, right? So it's the same, when I wrote this formula here, x of t, y of t, r prime of t in the bars, I didn't say whether it was 2-dimensional or 3-dimensional or 4-dimensional. That shouldn't present an issue for us anymore at this point, right? And that's kind of the point. Are there nice pictures in this section? I don't think so. I don't remember any good ones. Okay. So I'm going to skip that. and move on to the next part. Line integrals of vector fields. This is what Aaron asked me at the beginning. Remind me what a vector field is? Okay. This takes a little bit of time. So here's their example. They say, hey guys, here's a curve in space. The curve is C, right? And suppose C has the parameterization R of S. It says show R. Oh, okay. Well, R, by the way, as I move along, do you see what R is? R is the location, the position vector. Yeah, that's what it's been the whole time, right? R of T. All right, let's get rid of R for a minute. Now, you guys remember T. T was the collection of unit tangent vectors on C, right? There are tangent vectors all over that curve. What you are not familiar with yet is this F. F is a vector field. Why F? What do you think F stands for? Field is a good guess. I don't think so. Well, maybe it is.
Force.
I think it stands for force. I think that probably this particle, or planet, or whatever it is, as it moves, is being acted on by some force, right? I mean, what kinds of forces? Well, we mentioned gravity and we mentioned electric, and I'm sure there's others that you've studied and will study that's part of the reason that this is in the calculus book in the first place, right? And now, are you guys comfortable with this? Well, they're showing the force. Here, show the force on C. There they are. Show the unit tangent vectors on C. There they are. Do you notice anything? Me neither. Let's try again. Here, let's move around. Do you notice anything? Well, they're different, right? F and T are different. Sometimes F dot T is positive. Sometimes F dot T is negative. They have this little chart up here that tells me, ooh, look at all these. Can I get it to equal 0? What would that mean if F dot T is equal to 0? Then they're orthogonal, right? So that's kind of like a special situation when that happens, when the force is orthogonal to the velocity, right? We know that the velocity is in the direction of the unit tangent vector, right? Are you guys okay with this equation up above here? Well, for any particular F and T, and let me get a good one. I don't like that one. I like that one, okay. That's not a bad one. There, that's the one I'm going to reproduce. Here we go. So right over here on the side, I'm going to draw, just like they have, a green T. I'm not going to draw the curve. And I'm going to draw a red F. And I'm going to draw an angle theta. And what's the relationship, guys? There's some equation about the cosine of theta. Yes? Thanks for all your Calc 2 teachers. They were just outstanding. F dot T over the length of F times what? The length of T. Yeah? You've seen this before? Yeah. Great. But of course, what's the length of T? Now I blame your Calc 3 teacher if you missed that. Why is it 1?
Because it's a unit vector.
T is always a unit vector. Yes? Okay. So that means that we can just whoop that out, and we can say that F dot T is another way of writing F cosine theta. And that's the equation that they're writing there. Well, not quite F. I need magnitude of F cosine theta, right? Magnitude of F cosine theta is replaced by F dot T. Interesting. Notice when the dot product is 0, that's when the cosine is 90 degrees, because the cosine of 90 degrees is 0. Okay. Well, let's see where this is going. Well, where this is going is this. They say we can write the line integral of an entire vector field using that notation. Wow. So we're going to be talking about this. Big F being a vector field dot big T ds. What the heck does that mean? It says that the curve is parameterized by arc length, t is the unit tangent vector at each point, and the line integral is this. So you know what's going to happen, guys? I'm going to have to remember some of my Calc 3, right? I'm going to have to compute this unit tangent vector again. I'm going to be given an f, and supposedly this is going to be valuable. Well, it is valuable. It is valuable. And I like that your book right away says, okay, let's not only show them how to do it, let's show them a little why you might want to. A common application of line integrals is computing the work done. Okay, you physics graduates and students, how do you define work? Force times distance. There we go. So the work done as we go from A to B, distance along the x-axis, right, is work equals Fxd. Fx is the force of, projection. Yes, yes. Now I see it. This F cosine theta, that's Fx, right? So if I want to compute work, you told me work is force times distance. Well, what if I'm only moving a little tiny distance like delta x? This would be the work over a small interval, right? Yes or no? Okay. Well, if that's the work over a small interval and I say, let's compute the work as we move along a curve, it might not surprise you to say, oh, we'll just add all those up and then we'll appeal to my man Riemann. Riemann, right? It's a Riemann sum and therefore it's going to become what? An integral when you take the limit, right? Yes, this is very much a hand-waving argument, but this is good. Because if you understand that, then you understand that that's this, right? Wait a minute, wait. What's the progression? You told me that's work. The delta x becomes a dx, but instead we go this route and do the dot product, and we're going to do a line integral. And that's going to be my new convenient way to calculate work. Line integrals calculate work? Wow. Let's see an example. Here we go. Oh, too bad that the recording didn't quite catch that. It was close. See the little green arrows? All right. Anyways. We need an example. So here we go. Suppose a particle moves along a parabola. Math books love the bug on the parabola. And let's keep it real simple. Let's go with y equals x squared. Okay, so my particle's moving along. Let's say from A, which is -1, 1, I guess, to point B, which is 2, 4. Find the total work done if the motion is caused by the force field. So let me give you the vector field. F will be defined to be, well, let's say that it's this. It's x squared plus y squared, comma, and let's say that it's 3x squared y. And is this at all, is this at all reasonable that that would be the force field? I have no idea. I'm going to guess not. Okay? But let's say it is. So, well, I guess we can at least say a little bit. Let's draw a picture. Pictures help. So I tell you what, I know how to draw a parabola. From point A, 1, negative 1, it goes down to 0, 0, and then it goes up to 2, 4. So picture a parabolic roller coaster at Cedar Point. Just curious. When you plug in negative 1, 1, what's the force? I guess the force, f of negative 1, 1 would be, 2, comma, 3, right? So I could do that, 2, comma, 3. So my force is like that at the start. It's not really helping it very much. What about when I plug in f of 0, 0? Oh, well, then there is no force. What if I plug in f of 1, 1? Oh, same thing. 2, 3. So I still have that force going on. And then at the end, f of 2, 4. 4 plus 16, is that 20? Comma, 12 times 4. Yeah, 48. I don't feel like drawing that one, guys, but right? No, it'd be 12, yeah, something like that. All right. Realistic? I don't think so. But how do we compute it? So I guess, I can do this. I can say, oh, and I should say one more thing. We need units for this to be at all. So maybe I'll do one more assumption. Let's assume that the arc length is measured in meters. Why? Because it's a roller coaster? No, that's not why. And force is measured, do you know what I'm going to say? Newtons. Why am I saying this? Ah, yes, because the joule is equal to, right, a Newton meter, right? Yep.
So is like the force field basically representing gravity or electromagnetism?
It's something weird, yeah. I think it's psychic energy, actually. But yeah,
That's kind of
yes,
like what's
something's
going on.
moving the particle and acting on it, and it could be gravity, if you want to call it that. But this is weird gravity if it is, right?
Yeah, it's not.
Yeah, it's not gravity.
Another universe.
Yes, yes. So, but interesting nonetheless. All right, so how do I do this? Well, one thing that would help, I guess, is if we parametrized the curve, right? This is important, right? Because your initial, well, we have the initial form up here. We can just do f dot t, but I'll need a parameterization of the curve, right? Of course, I told you an easy way to do that, right? So we can do, to parameterize the curve, to parameterize C, let x of t equal t, and let y of t be what? T squared, because y equals x squared. So that works pretty well. So now that means let's see, well, r of t, right? You could say is t comma t squared, right? And so what else do I need? I guess I need r prime of t, right? What's r prime of t going to be? 1 comma 2t. And I guess I also need the length of r prime of t. Only it's not going to be a nice number like the square root of 2 anymore, is it? It's going to be the square root of 1 plus 4t squared, correct? Yeah, I think so. So let's work out what we have here. Well, I guess maybe I should rewrite f in the same way, right? I mean, okay. I'm running short of a room. Well, we can try and put it here. Integral over the curve of f dot t. Now, what's t again? Do you remember what t is? Yeah, how do you get it? Take r prime and then divide by the magnitude of r prime. So I have everything I need, right? Right there. Okay? And then I have ds. So let's see. If we do this, let's see. F dot t. Got to be careful here. This is going to be integral. Okay. Oh, one thing I didn't do. I didn't say what the range of t is. I should have done that. Well, that's easy because we said x is going to be t, so we're going from -1 to what? To 2, right? So the integral is going to go from -1 to +2. And when I say I'm doing f dot t, it's going to be t squared plus t to the 4th, right? Because that's t squared squared, comma 3t to the 4th 3t squared t squared. Oh, which is going to be 3t to the 4th. Dot. What am I dotting this with? Well, t, right? And t, of course, is 1 comma 2t divided by, well, it would be the length of r prime of t. But the funny thing is, you might remember what I told you, is that when you substitute in for ds, you can do that if you change it to r prime of t dt, right? So the r primes are going to cancel. Yeah? I mean, whatever it is, I computed it. I don't need it, though. That's kind of the point. All right, so what do we have to integrate? We have to integrate from -1 to +2. Oh, we need the dot product, guys. What's the dot product going to be? Well, this dot product, you get t squared plus t to the 4th from that first piece, right, times 1. And then this is 3t to the 4th times 2t, so that would be plus, wouldn't it be 6t to the 5th? Yes? And then Marvin, I'm just like you, I ran out of room. So where am I going to do this? I guess on the next page we'll finish up. Let's see. I have so far the work equals, and if I integrate this, I have 1/3 t cubed plus 1/5 t to the 5th, plus t to the 6th, right? And we go from -1 to +2. Which is pretty nice. And as I go from -1 to +2, I guess I get, well, let's see. Plug in the 2 and I get 8/3 plus 32/5 plus 2 to the 6th is 64. Then I have to subtract, well, what happens when I plug in a -1? You just have to watch your signs now, right? So I'll be subtracting, let's see, -1/3 plus, well, I'll say -1/5. But when you put a -1 in here, you get +1/6. And if you subtract that all carefully, without going through the details, let's say you get 363/5, which is 72, well, it's exactly equal to 72.6 joules. 72.6 joules is the work done by that integral. Okay. Now, interesting idea here next. Sometimes, so what was the original problem? The original problem was, let's see, integral, well, again, it was f dot, and we said t ds, right? But t we wrote as r prime of t over length of r prime of t, right? ds. And of course, ds we wrote as length of r prime of t dt. Yeah? That's what we did. So, I guess if I got rid of these, which I did, what I really dotted together, no, I'm not saying it right. Let me pause for a second and think. I guess this was the point that I tried to make, right? F dot t is great, but you notice it's really just f dot r prime dt, because in this case, right, because we have the unit tangent vector, then the speeds cancel. The length of the r prime cancel. Oh, yeah, this is a nice example. You wondered where that 3/2 came from for your physics? Well, they're going to talk about it there. That's kind of fun stuff. Okay, but what I wanted to mention a little bit was the circulation and flux of a vector field. So circulation, we're talking about kind of movement in the direction of r prime. And then flux, we're talking about being orthogonal. Okay, so here's their definition of circulation. Circulation. Oh, that's funny. I just saw that integral. Wasn't that the definition of work? Right? Okay, we're going to call that circulation. That makes sense? That's good. It makes sense to you. I'm happy. Now, then they're going to talk about flux. Oh, by the way, what do we have here? Well, we have an example of a three-dimensional flow. Find the circulation of the vector field zx negative y on this tilted ellipse. So draw the unit tangent vectors. There they are in green. So now, see these red vectors? These red vectors are from the vector field. And so what happens is we are projecting, when we do the dot product, right, onto the green vector. Boy, it's hard to see that. But, I mean, maybe you could see it. Oh, maybe I can make it easier to see. That's what I need to do. Yeah. So see how these red vectors are definitely not even in the plane that has the green vectors? The green vectors, of course, being tangent vectors, are in the plane of that oval. Yeah, now I can see why they gave me this applet, because that shows it. So what do? We want to take this red vector and project onto that green vector. And so we do, right? And so those blue vectors, which are scalar multiples of the green ones, that's what's really going on when we talk about circulation. Okay. Then we're going to talk about flux. So same game here. For the flux to be perpendicular, you'll notice, what did they draw? Oh, they drew the normal vector n. Remember that guy? This is lowercase n. We used capital N if we had what? Unit vector was capital N. Okay. So, yeah, this is actually really fun. They're playing the game. Okay. Can we find one where it's... Oh, yeah, there it is. When it's 0, that would make them orthogonal. But the question is, F. F is red. Is it pointing outward on C or inward on C? That's kind of the idea. When it points inward, it's going to kind of like being... Remember area of a curve? But if you're below the x-axis, then what happens? You subtract. Well, same thing here. Flux, we're going to be measuring kind of what happens with respect to this curve. Am I moving inward or outward? Okay. Here's another view of this thing. Oh, okay. So here's, yeah, we had the 2D view, but the real picture is this, guys. So N, it says, is T cross K. Well, that makes sense. It's perpendicular to the unit tangent vector, but we're going to cross it with K, and that's what little n is. All right, let's move around. Nice. Let's show those projections onto the normal vector. There you go. So see, F here is opposite of the normal vector. And that's why you have a negative contribution. Whereas someplace over here, the force, the projection of the force is onto the normal vector, and that gives you a positive contribution. Okay? So maybe that'll help. Well, we're at 11:50. I am out of time. Oh yeah, cross products are back. Well, you'll have fun with that tonight. We'll see where it goes.